How's it going, everybody? Right about now, we're going to cover Chapter 3, Basic Concepts of Probability, just to go over some of the learning objectives. So we're going to learn the concept of sample space associated with a random experiment. We're going to learn the concept of events associated with a random experiment, learn the concept of the probability of an event, learn how some events are naturally expressed in terms of other events, and learn how to use special formulas for the probability of an event that is expressed in terms of one or more other events. So first thing we want to talk about is sample spaces and events. So a random experiment is a mechanism or a tool that we use that will help us to produce a definite outcome that cannot be predicted with certainty. Okay, so there's something key in there. We cannot predict it with certainty, but it allows us to produce an outcome. Okay, this is a random experiment. The sample space associated with a random experiment is the set of all possible outcomes. So for example, if we were testing individuals for COVID-19 and we were giving them some medicine, right, for that, the outcomes of giving them that medicine could be they either get better, they either stay the same, or they get worse. Okay, so those could be the sample space or the possible outcomes. An event is a subset of the sample space. Okay, so a subset of the sample space being within that sample. An event E is said to occur on a particular trial of the experiment if the outcome observed is an element of the set E. And what we mean by an element of the set E is that it is contained within that set. Okay? It is contained within that set. So we have an example here. Sample spaces and events. Find all outcomes for a 3-child family. Okay? So what are the all outcomes for a 3-child family? So basically we do a probability tree here in order to see all the possible outcomes. So a family, all right, their first child could be either a boy or a girl, right? And then from there you would have your second child outcomes and your third child outcomes. So you could have all 3 boys, you could have a boy, girl, or you could have a boy, boy, girl, you could have a boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. And those are all of our outcomes that are listed here. So essentially we have 1, 2, 3, 4, 5, 6, 7, 8 potential outcomes. Know that there are a couple of outcomes that are repeated here. For example, if we have boy, girl, boy, okay, we have a boy, girl, boy, or girl, boy, boy here, which would almost be the same thing. Okay. Now if we take a look here, it says tree diagram for the 3-child family. The line segments are called branches of the tree. The right ending point of each branch is called a node. The nodes on the extreme right are the final nodes. From the tree, it is easy to read off the 8 outcomes of the experiment. So the sample space is reading from the top to the bottom of the final nodes in the tree. Okay, so we have all of our possible outcomes here. Probability. Now, the probability of a particular event, okay, I'm not sure why that moved there on us, but if we go ahead, the probability of an outcome E in a sample space S is a number P between 0 and 1. So when we're talking about probability, it's either 100% probability that an event will occur, which would be representative of 1, or it could be 0%, there's no possible way it could happen, or it could be anywhere in the middle from 0 to 1, right? 0 to 1 would be those decimals, and we can always convert decimals to percents. So the value P equals 0 corresponds to the outcome E being impossible, and the value P equaling 1. And then we have, corresponds to the outcome E being certain. The probability of event A is the sum of the probabilities of the individual outcomes of which it is composed. So sum of the probabilities here, we would add them together. Probability of E, probability, E sub 2, E sub 1, E sub 2, E sub 3. Those are all the different events that could occur. Okay? There we go. Complements. So the complement of an event A in a sample space S is denoted by A to the C power, is the collection of all outcomes in S, the sample space, that are not elements of the set A. It corresponds to negating any description in words of an event A. Here's our probability rule. Basically, we say that the probability that A to the C power is going to happen, the probability that the complement of an event would happen would be if you take 1 and you subtract from it the probability of A. Okay? Another way of denoting this to the C power here, you could call it like A naught. So it's not the probability of A, it's the opposite of the probability of A. So for example, let's say the probability of A was 90. There was a 90% probability that an event would occur. Then this would be 10%, right? 90%, 10%. We would get that by taking 1 and subtracting 0.9 from it and getting 0.1, which would be 10%. The two events connected with the experiment of rolling a single die are E, the number rolled is even, and T, the number rolled is greater than 2. Find the complement of each. So here's the solution for it. So the sample space, when you're rolling a die, you can roll either a 1, 2, 3, 4, 5, or 6. So there's 6 possibilities. Okay, and we have different outcomes for each piece here. So E is the number rolled that's even, and we know that if you roll a 2, 4, or a 6, that's going to produce an even number. In T, the number rolled is greater than 2. The only values that satisfy that are 3, 4, 5, and 6. So the complement, all right, are 1, 3, and 5, right, for E, because those are odd numbers, the opposite of even numbers. And then the complement of T would be 1 and 2, because those are numbers that are equal to or less than 2, where before we were just talking about greater than 2. Now we have an intersection, so we denote the intersection with this upside down U here. The intersection of events A and B, denoted A intersection B, is the collection of all the outcomes that are elements of both the sets A and B. It corresponds to combining descriptions of the two events using the word and. To say that the event A and B occurred means that on a particular trial of the experiment, both A and B occurred. For example, if we had a classroom of students and I wanted to know what is the probability that a student in the class has blue eyes and brown hair, okay? That would mean that there's the intersection. We have only the individuals that have both blue eyes and brown hair, which is different from what we're about to talk about, which would be the union. You know, what is the probability that a person in the class has blue eyes or brown hair, okay? See how that's different? That's a larger group of people because it's either or, where this is I need to have both. The intersection needs to happen. They have to both have the same eye color and both the same hair color. There's an example here, another one that you can use. In the experiment of rolling a single die, find the intersection of E intersection T. So the intersection of those two, we know that E is the even numbers and T represents those greater than 2. Numbers that are even and greater than 2 are 4 and 6, so that's why 4 and 6 are in the set that is the intersection between E and T. Another piece that we use, so this is what you call a Venn diagram, and I use a Venn diagram a lot to discuss intersections and unions. So an intersection would be the piece in the middle here. All those values that fall in set A but also fall in set B are the intersection, which would be this point here. The union would be those things that fall in set A and set B separately, but we include all in one as together. So it would be a larger grouping. When we talk about mutually exclusive events, so I'm going to move my picture up here for you. When we talk about mutually exclusive events, A and B are mutually exclusive if they have no elements in common. So for A and B to have no outcomes in common means precisely that it is impossible for A and B to occur on a single trial. So we can't have the intersection. Mutually exclusive means the intersection is not possible. Events A and B are mutually exclusive and only if the probability of A intersection B is 0. See what I'm saying? You can't have A intersection B. Any event A and its complement a to the c power are mutually exclusive, but a and b can be mutually exclusive without being complements. Okay. This is now we're talking about the union. So the union is this piece right here, and if we slide down to see, this is what I was talking about earlier with respect to the Venn diagram here. If you want to go back to the slide, there's an example prior to this slide that will go over it for you. But basically the union is the whole thing, where the intersection was just the middle here. The union is this, and we're including everything. So if I want the people in the class, hey, listen, if you have blue eyes or blonde hair, you're good. You can go outside and go to recess, all right? But, you know, all those other people can't. So this would represent blue eyes, blonde hair. All those people that have either blue eyes or blonde hair can go to recess, right? Or it could be, no, you can only go to recess if you have blue eyes and blonde hair. If you just have blue eyes, that doesn't count. You can't go, okay? If I said that, that would be the intersection. The earlier piece would be the union, okay? The additive rule of probability here, when we have the union, we have to actually subtract the intersection once we add those two pieces together. The reason we have to subtract the intersection is we're counting the overlap twice. We're counting it in the probability of A and the probability of B. If you need some assistance, we can go ahead and go over this, you know, in class during our session, either, you know, this Wednesday or next Wednesday. Conditional probability, okay? The probability of A given B, that means if we have an event that is given in this situation, this would be the formula that we would use, the probability of A intersection B divided by the probability of B. Formula for independent events, so if you have the probability of A intersection B, we can just multiply the probability of A times the probability of B. These are all formulas that you should be writing down and using and being able to differentiate between. Keeping notes, you know, for the final exam in areas like this would be important. So in this particular case, a single fair die is rolled. Let A equal set 3 and B equals let A equal 3 and B equal the set that includes 1, 3, and 5. Are A and B independent? So in this example, we can compute all three probabilities. Probability of A is 1/6. The probability of B is 1/2. Okay? And the probability of A intersection B is also going to be the probability, all right, of 3, which is 1/6. Okay? Since the probability of A and the probability of B equals 1/6 times 1/2, which equals 1/12, and it is not the same number as the probability of A intersection B, then the events A and B are not independent. Okay. A few more tree diagrams here to go over. Some probability problems are made much simpler when approaching using a tree diagram. Anytime you can draw a picture, it's going to be helpful. So here's an example. A jar contains 10 marbles, 7 black and 3 white. 2 marbles are drawn without replacement, which means the first one is not put back before the second one is drawn. What is the probability that both marbles are black? What is the probability that a marble is black? What is the probability that at least one marble is black? We can use this tree diagram to figure this out, right? Probability of the intersection, probability of the intersection, intersection. We multiply them, and we can get our answers here. Okay, just in review, some key terms that we went over here: knowing the sample space, the events, the probability of an outcome, probability of an event, complement of an event, intersection of two events, union of two events, what mutually exclusive events are, conditional probability, independent events. Okay, having a solid understanding, you know, of these key takeaways is very, very important as well. So my thought would be during our class on Wednesday, which would be June 3rd, you know, we'll go over any questions that you might have here. Remember, I can be available for one-on-one sessions if it's needed. You will be quizzed on, I believe it's 2 and 3 at the end of this week. So it's important that you take a look at that. Okay. We'll see you on Wednesday. Thanks.